In this video, I'm going to be introducing the concept of the antiderivative and the process called indefinite integration. So in this course, we've learned how to find the derivative if we're given a function. Sometimes what we want to do, however, is if we're given the derivative, we would like to find the function that it came from. Therefore, what we're really doing when we find this antiderivative is we are reversing the process of finding a derivative. In other words, we're undoing the derivative. So as an example, let's say that we have this function 2x, and let's suppose that 2x is the derivative of some other function. Well, if you think about it for a moment, you might realize, well, that function, which we're going to write with a capital F to represent the antiderivative, would be x squared. Now, how did I come to that? Well, I just sort of asked myself the question, if this is the derivative of something, and I know what the power rule is, how could I undo the power rule? In other words, this 2 would have had to have been an exponent. And so x squared actually fits the bill. If I take the derivative of this function, I get 2x, and that is equal to my function here, f of x. So all we're doing is undoing the derivative. So let's do another one. Take a moment and see if you can figure out if this is this function is the derivative of some other function. What would that function be? What would capital F of x, the antiderivative of f, have to be? Well, if you said x cubed, you would be absolutely correct. And you can show that this is true by applying the power rule for finding derivatives. F prime of x, we bring the exponent down in front, multiply it by x, and subtract 1 from the exponent. So with simple problems like this, it's not too difficult to find the antiderivative, but we're going to develop a process or a formula for finding it for even more difficult ones. A function may have an infinite number of antiderivatives. So take a moment and think about what the antiderivative of this function would be. So we have f of x is equal to 4x cubed. Using the same logic that we used in the last two problems, you would come up with x to the fourth, right? And so we would say that this was the antiderivative because the derivative of this is equal to 4x cubed. But there's a little bit of a problem. Why couldn't my antiderivative be x to the fourth plus, let's say, 1? Because the antiderivative of this is also 4x cubed. Well, why couldn't the antiderivative be x to the fourth plus 8? The antiderivative is also 4x cubed. Why couldn't the antiderivative be x to the fourth plus any constant? Because x to the fourth plus any constant, no matter what that number is, the derivative is always x to the fourth. So all of those are completely legitimate antiderivatives. That's why we say we have a collection of functions. The antiderivatives are a collection of functions. And so since we don't know what the constant is, in this first case, we're assuming the constant is 0. Well, maybe the constant is 0, maybe it's 1, maybe it's 8, maybe it's 1/2, maybe it's a million, maybe it's negative 0.2. We don't know. So what we do is we always just say plus some constant c. Plus some constant c. So when we're finding the antiderivative of a function like this, we'll say, okay, the antiderivative is x to the fourth plus some constant c. And so we're going to do that for all of the rest of the problems that we do. Let's just do another one real quick here. Let's just say that I had f of x let's go back to one that we already did before, is equal to 2x. Well, now we would say that the antiderivative is x squared plus some constant c. So it's very important that you always add this plus c. We don't know what c is, and eventually we'll find ways to determine what c is, but for now we just add the plus c for some unknown constant. All right, the indefinite integral. This right here is what we call the indefinite integral. The indefinite integral of a function f of x with respect to x, and stands for the set of all antiderivatives of f. Thus, the integral of f of x dx is a collection of functions. It is not a single function or number. So basically, think of this as a notation that tells us to find the antiderivative. Okay, so instead of going back to this problem here, instead of saying find the set of all antiderivatives of f of x is equal to 3x squared. Instead of saying that, we can simply say the integral of 3x squared dx. And this means the same thing. This means find the set of all antiderivatives of 3x squared. That's what the notation with this little squiggly s-like sign and this dx. We'll talk more about what this dx means in a future lesson. But these come as a pair, okay? The squiggly line, which is called the integral symbol, and the dx. In between those is the function that we are looking for the antiderivatives of. So, with that in mind, we have a couple of rules for finding antiderivatives or indefinite integrals. The first one is the power rule. Now, just like there was a power rule for derivatives, this is the power rule for finding antiderivatives. And what it says is, let me write it a little bit bigger over here, find the set of all antiderivatives of x to the n. Well, the rule says we take x and we add 1 to the exponent. So remember, when finding the derivative, we would subtract 1. So it makes some sense that we might add 1. And then we divide by the n plus 1, plus c, of course. And so the important part is we have an n plus 1 here, and that goes down here in the denominator. So let's see how that works with a function that we've already done. So what this is asking us to do is to find the set of all antiderivatives of 3x squared. Well, we already determined that f of x was x cubed plus c. But let's apply the power rule to it. If we apply the power rule, we're just going to bring down the 3. Applying the power rule to the x squared, what would we do? We would add 1 to the numerator, to the exponent. That would give me a 3. And then we would divide by the exponent, which is 3. All right. Well, what happens to these 3's? They cancel out. And what we're left with then is x cubed. And then we add the plus c. And so that gave us what we already developed a formula for intuitively. But we're not always going to be able to do it intuitively, so it's going to be handy to have this little formula. Also notice with the formula that n cannot be equal to -1. If n is -1, we have this special formula, which has 2 different versions. So the integral of 1 over x dx is equal to the log of x, which is the same as the integral of x to the -1 dx. And we'll do a couple problems with those in here in a second. Okay, here's another one. Let's apply our power rule for finding antiderivatives. So what I like to do, here's a nifty thing. Whenever you have a constant, you can just bring that, you can just bring that out in front of the integral sign. So it's kind of like you have 2 times the integral of x dx. Just get the constant out of the way. Now we're going to apply the power rule to this. And when we do that, we're going to get 2 times x, add 1 to the power, and then divide by that. The 2's cancel. You're left with x squared plus c, which we already knew because this is one that we also figured out before. So here's some examples we have not done. And so find the set of all antiderivatives of x to the 4th. We simply add 1 to the exponent, x to the 5th, divided by 5, plus c. Now, the way that I prefer to write these is 1/5 x to the 5th plus c, but either way is correct. Here's one with a negative power. So applying our rule to x to the -5 dx, we're looking for the set of all antiderivatives. So I'm going to add 1 to the power. That would make it a -4 divided by -4 plus c. And this would be a little bit better written as -1/4 x to the -4 plus c. Now, I'm going to say let's leave this as a negative exponent only because the original problem had a negative exponent. So I like to leave my answers in the same form as the original problem. 3x to the -1. Okay, let's bring the 3 out in front of the integral sign, and we have x to the -1 dx. So remember, this was that special rule. This can be written like this, 1 over x dx. And the rule said we would have 3 times the natural log of x plus c. And this also makes sense because remember what the derivative of the natural log is. It's 1 over x. So the antiderivative of 1 over x is log of x. They undo each other. With this one, let's bring this out, bring the 7 out. And once you bring the 7 out, you see that you have a 1 over x dx, which is clearly another example of this log rule. 7 times the natural log of x plus c. 2e to the x. So 2e to the x. The antiderivative of e to the x, I didn't give you a formula for this, but the antiderivative of e to the x is, guess what? E to the x. And the reason is, what's the derivative of e to the x? It's e to the x. Since e to the x is its own derivative, it's also its own antiderivative. So the answer to this is simply 2e to the x plus c. Now in this one, we have 3 different terms. We have the first term, the second term, third term. We simply apply our rules to each term. So we don't have to write it this way, but it's kind of like we're saying 4 times the antiderivative of x squared dx plus 5 times the antiderivative of x minus 1 times the antiderivative of dx. Now, I'm not advocating that you write it this way, but you can think of it as 3 different problems. That one, and that one, but we're just going to apply the power rule to each part of this. So we would have 4x cubed over 3 plus 5x squared over 2 minus 1x. Now you may be saying, how do I do this one? Well, there's no x in this. That means it's like x to the 0 power, right? So the integral of dx is the same as the integral of x to the 0 dx, because remember, anything to the 0 power is 1. And so if we apply the power rule to this, we get 1 over 1. And then let's just clean this up. So we have 4/3 x cubed plus 5/2 x squared minus x plus c. Okay, in this next one, we have 3 terms again, 1, 2, 3. Now, I'm not going to write it out term by term again, let's just apply the rules to each one of these terms here. So this would be 5 e to the x is the antiderivative of the first term. And then we have minus 4x squared over 2 is the antiderivative of the second term, plus 2. And again, 2 is really like 2x to the 0, but we would just write that as 2. That becomes 2x plus c. So cleaning this up a little bit, I would have 5 e to the x minus 2x squared plus 2x plus c. Now, when we learn how to find derivatives, sometimes we needed to clean up the derivatives a little bit. We needed to do some algebraic manipulations. Well, that's the same thing here. So we want to rewrite this in a form where we can actually apply the power rules. So when you have radicals, you want to rewrite them as rational exponents. So remember we said that square root of x is the same as x to 1/2. And here we have the cube root of x is the same as x to the 1/3. So I'm going to go ahead and rewrite this as the integral of x to the 1/2 plus 3x to the 1/3, put that all in parentheses, dx. Now we can apply the power rule to each one of these terms. So we would have x to the 1/2 plus 1 would be 3/2 divided by 3/2 plus 3x to the 1/3 plus 3/3 would be 4/3 divided by 4/3 plus c. And of course, we're not going to keep it like this. We're going to take this denominator and we're going to take its reciprocal and multiply by the numerator in both of these cases. So we would end up with, this would become 2/3 x to the 3/2. And then 3/4 times 3 would be 9/4 x to the 4/3 plus c. We want to do the same thing with this one. We want to rewrite it in a form where we can apply the power rule. So we don't want the x's in the denominator. So we're going to have the integral of, now 1 over x is the same as x to the negative 1. And this would be plus 3x to the negative 2 minus 2x to the negative 3. And then applying the rules to these, we would have the natural log of x plus 3x to the negative 1 over negative 1 minus 2x to the negative 2 over negative 2 plus c. And that then would be the natural log of x minus 3 over x. And then we have double negatives and the 2's cancel. So that's going to be plus 1 over x squared plus c. Now in this case, I'm putting the x's back down in the denominator because that's the way the original problem was written. All right. That is the basics of how you find antiderivatives, and that should get you through most of the homework. The next video that I'm going to do will be a few applications of antiderivatives.